In this second lesson on moments, we're going to have a look at objects which are in equilibrium. Now, when we say equilibrium, just like in other bits of mechanics, what we mean is when the forces are balanced. So there's no net force up, down, or left or right, or at any other angle. So it is not accelerating. Okay, could be moving, but it's not accelerating. Most of the questions that we will look at in this section, it won't be moving at all either. Okay. So here I've just got like a beam, and then I've got two supports. So maybe this is like a plank of wood or something like that. We're going to describe it as a uniform rod. Okay. Now, when we say uniform, the important thing there is uniform means that it is symmetrical. So its center of mass is exactly halfway along it. Okay. So when we say uniform, it means it's like the same thickness all the way through it, like that. Okay. Rather than kind of like some sort of wedge shape like this. Okay, so here the center of mass would be in the middle. Here the center of mass would probably be, I don't know, about there, wouldn't it? Okay. So it's a uniform rod of length 3 meters in total and weight 20 newtons. So I'm going to draw the weight on. So if I draw the weight there, it's exactly in the middle of the plank. So that's 20 newtons, which means this distance here is halfway along the plank. So that's 1.5 meters. And we've got to calculate the magnitude of the reaction force at each of the supports. So there is a force here. So this support is pushing on the plank with a reaction force. I'm going to call it RC. And there is a force on the plank here, a reaction force. That's A, so RA. Now we've got to try and calculate what RA and RC are using the fact that it's in equilibrium. Now the easiest place to start, rather than thinking about moments at all, is actually to just think about the forces. So if we look at the forces up and down, we can say that RA plus RC must be the same as 20 newtons, because the total force up must be the same as the total force down. So that's one place to start. Obviously we can't solve this yet because we've got two variables. Now what we can do is we can take moments about a point. Now we can actually take moments about any single point on here, and what I mean by take moments about is imagine that a point is the pivot. So if we do moments about, we'll do moments about A first of all. Okay, so if I put my pivot here and imagine that I was letting it pivot around that point. Now the moments here, I've got 20 newtons here. This is going to make it go clockwise. So I've got 20 times 1.5, because it's 1.5 meters away, anti-clockwise. That must be equal and opposite to the moment from RC, which is making it go anti-clockwise. So that must be equal to RC times the distance away, which is 2 meters. Okay, because this moment must be the same as this one because it's in equilibrium. So if I then solve this equation, I can see that RC is 15 newtons, which then, if I look at this equation here, RA plus RC is 20, so that must mean that RA is 5 newtons. We've got to our answer. Okay. Now we could actually take moments about anywhere else. So let's try somewhere else. Let's do moments about C. Okay, so if I took moments about here, and use this as my pivot, now I wouldn't have to worry about RC because this is distance 0 away. And this is the same reason we didn't worry about RA when we did moments about A, because the distance is 0, so that doesn't provide any moment. So moments about C here, I've got 20 newtons times this distance here would be 0.5 meters, because this whole length here is 2 and this is 1.5. So I've got 20 times 0.5, that would be equal and opposite to RA times 2 meters, which I can then solve to give me RA is 5 and then RC is 15 using the first equation. Let's see if we can come up with another one. We can, in theory, you can take moments about any point along this plank, okay, and you would still be able to solve it. If we did moments about B to the far end of the plank, so here, then we could do that as well. So we would have RC times 1 meter. That's providing a clockwise moment. We would also have RA, that's making it do a clockwise moment as well. So we'd have plus RA times the distance of 3. That would be equal and opposite to this force, which is making it go the other way. So that'd be 20 times the distance is 1.5. And now this one's not quite as easy to solve because I'd end up with RC plus 3RA equals 30. But I could then solve this and this one simultaneously to find RA and RC, and you'd still get the same values. So picking some points makes it quicker than others, but you should always be able to get there by resolving up and down and taking moments about a point. If you've got more unknowns, then you might just have to take moments about several points. Okay, here's one for you to do. Perhaps have a go at this one yourself first, and then I will go through it. Okay. So for this one, a uniform beam again, so the centre of mass is exactly halfway. So let's put that on here. Now notice that this time I've given you the mass rather than the weight. So the weight is going to be 10g, or 10 times 9.8. Support C is 1 meter from A. So this is 1 meter. And support D, let's actually use these arrows, shall we? Support D is 2.8 meters away. Find the reaction in each of the supports. So we've got RD and RC. Okay. Now the first thing to do is to resolve up and down. So we can say that RC plus RD must be 10g. Okay. You don't have to do this step, but because you could do moments about two different points and solve them simultaneously. But this is always an easy equation to form. Now let's do moments about a point. I'm going to do moments about A, I think. I'll do it a different way in a minute as well. If I do moments about A, then I've got RC times 1 plus RD times 2.8, because they're both trying to make it rotate anti-clockwise. They must be equal and opposite to 10g times this distance here, halfway along, which is 1.5. So I get RC plus 2.8 RD equals 15g. Now if I solve these two equations simultaneously, you can just use your calculator to do that, remember. Your calculator has a mode where you can solve simultaneous equations. I'll get RC equals 70.8 newtons and RD is 27.2 newtons. And those are my answers. Now other places you could take moments about. Perhaps let's do moments about C. It's a nice easy place to do moments around. So we put it here. Then we would have 10g times this distance here, and that'd be 0.5 because it's 1.5 along because it's uniform. So that'd be 0.5. That would be equal and opposite to RD times this distance here, which would be 1.8 meters. And if we solve that, then we get RD equals 27.2. And then we can stick that into this first equation and solve it again. Okay. But the point here is that you can take moments about any of these points, and you'll be able to solve it. Okay, so a slightly different style of problem here. So a uniform beam, so the centre of mass is halfway, of mass 40 kilograms. So let's just put that on straight away. So halfway there, so that's 40g. And length 5 meters. Okay, so the overall length is 5 meters. We'll stick that on as well. It is worth spending time making a diagram good and useful. Okay, and then each of these distances is 1 meter at the ends, so it's kind of symmetrical. When a man of mass 80 kilograms stands on the beam at point E, let's put his mass on as well, that's 80g. The reaction at D is twice the magnitude of the reaction at C. So this reaction force here is twice the size of the reaction force here. So if I was to call this R, then I could call this one here twice that, so 2R. Okay. By modelling the beam as a rod and the man as a particle, so when we model it as a rod, that means it doesn't bend or anything like that, and it's just, we don't have to worry about its size either, other than its length, it's just one-dimensional. Man as a particle, that means we don't have to worry about the size of the man. We can just treat him as just a single point with a mass. Okay. Find the distance A to E. So what I'm looking for is the distance from A to E. Okay, so that distance there, so I'm going to call that X. Okay. Now, it makes sense for the man to be on the right of the centre of mass because this reaction force here is bigger than this one. So he must be closer to this end than he is to this end. Okay, so in terms of the diagram, that makes sense to draw it like that. So let's try and see what we can work out. Let's resolve vertically first of all. So I've got R plus 2R equals 40G plus 80G, just looking at the vertical forces. So I could obviously set 3R equals 120G, or that would give me R equals 392 newtons. Okay, so I've actually worked out what R is already. Now we need to work out its distance X. Now we can take moments about anywhere on here. We could do it about A, C, E, the centre of mass perhaps, D, B. I'm going to do it about A just because I've measured my distance A to E as what I'm trying to find, as obviously being from A. So I'm going to do moments about A, but you could feasibly pick any point on here to do it. So moments about A, so I've got R times 1, that is a anti-clockwise moment, plus 2R times this distance here is going to be 4 meters, that's also anti-clockwise. They must be equal and opposite to 40G, that was the centre of mass, so that's halfway, so that's times 2.5, plus 80G times distance X. Okay, now I know what R is, so I can substitute that in, and I can solve this equation to find X. And if I do that, I get 3.25 meters. So I think that's the simplest way to solve this question. Again, you could do it in lots of other different ways. Maybe if you did moments about, let's just pick a random example, let's do moments about C. Okay, so if I did moments about here, so I don't have to worry about this force, I would have 2R times this distance here. So that's going to be 5 meters at minus 1 minus the other 1. So that's going to be 3. And that's the only anti-clockwise force. So that would have to be equal to 40G times this distance here. That would be 2.5 from there, but minus a meter, so that's going to be 1.5. So some of the distances become more or less complicated to work out. Plus 80G times, well, if this blue distance is X, this one here is going to be X minus 1 meter. So that's going to be X minus 1, like that. And then you could solve this to find X minus 1, and then obviously find X. So there's several different ways you can solve these problems. Okay, here's a problem with quite a different context to it. So this time we've got a uniform rod PQ. So that is this length here. So maybe this is just like a plank of wood or something like that. Is held in equilibrium at an angle of 50 degrees to the horizontal by a force of F, which is perpendicular to the rod. So this rod has obviously got some weight. So it wants to basically fall down and lie flat on the floor. But we've got a force, maybe it's a rope or something, holding it still. And it's perpendicular to the rod here. The rod has got a length of 3 meters. Let's just put that on. And a mass of 8 kilograms. So we've got that on there already. That's 8G. Okay, I'm going to make this a bit bigger as well. So this is 8G. And we've got to find out what force F is. Okay. Now to do this, we can use some of our skills from resolving forces on slopes. So this is 8G. We can resolve this into perpendicular and parallel like this. So this is going to be 50 at the top. And this force here is going to be 8G cos 50. And this force parallel is going to be 8G sine 50, just like we do for forces on a slope. Okay. Now, to actually find out what F is, because it's in equilibrium, if we take moments about point P, then the moments should be equal. So it's not rotating overall. So if we take moments about the point P, so about this point here, now remember, it's the perpendicular force times the distance. So F is easy. because that's already perpendicular, so it's just F times 3, force times distance. Now for this force in here, it's a little bit more complicated. We've just got to pick the perpendicular component. So that's 8G cos 50. Okay, that's a perpendicular force. So that the distance and the force are perpendicular. And the distance, because the centre of mass is halfway, this is obviously 1.5 meters. And now we've got an equation that we can solve. So F comes out as 25.2 newtons. And that's all there is to it. So a slightly different context, but just remember that a moment is either the perpendicular distance times the force, or the perpendicular component of the force times the distance. Here's a similar sort of problem. This time we've got a ladder leant up against a wall. We're going to do lots more ladder problems in some of the later lessons, but this is kind of an introduction to it. So we've got a uniform ladder, so its centre of mass is halfway, with mass 5 kilograms. Let's just put that on first of all. It says its weight, 5G. And then length 2 meters. Okay. Find the reaction force at the wall when the ladder makes an angle of 50 degrees to the floor. So this is 50. We can resolve this weight here. Okay, exactly the same as we do normally. So this is 50. This is 5G cos 50. Going that way. And then 5G sine 50 down that way. Now the reaction force at the wall, just like normal reaction forces, this is at 90 degrees to the surface. So I'm going to label this as RW for the reaction at the wall. Now there would be another reaction on the floor as well. So there'd be a reaction here. Reaction force on the floor. Okay, so this is the force that stops the ladder falling through the ground, and this is the force that stops it just sliding through the wall. Okay, there is a reaction force back this way. Now, we can resolve this reaction force at the wall because at the moment it's not perpendicular to the distances, because if what I'm going to do is I'm going to take moments about the bottom of the ladder, if we call this point A. So moments about A, the bottom of the ladder. So I've got this distance here, and then the perpendicular component. So that's 5G cos 50, it's the perpendicular force, times the distance, so it's going to be half the length of the ladder, so that's 1 meter. And now I need this component here, okay, because that is the perpendicular component. Again, you could draw it there, if that makes more sense. If we line that up there, you could draw it there. Okay, they're both the same thing, if that helps. You could draw that triangle instead. Now, if this angle here is 50, that means that this one here is 50, because they're alternate angles. We've got this Z shape like that. So that's 50 up there as well. So this component here is going to be RW sine 50. Or you could do it, if you're looking at this one here, you could say this is 40, and then it would be RW cos 40. But it's the same thing. So this is equal to RW, the reaction at the wall, sine 50, so that perpendicular component, times the distance, so that's this distance here, all the way up to that force, which is 2 meters, the whole length of the ladder. And then if I solve that equation, I get 20.6 newtons. Okay. So we're going to look lots more at ladder problems. Probably next lesson we'll look a bit more at ladder problems, and that tends to be a sort of thing that comes up a lot in exam questions as well. And we'll look at ones where we've got friction involved as well. So there's friction at the floor, or perhaps even friction on the wall as well, which makes things a bit more interesting too. Okay, so the last example I want to do is just one where, what if it's non-uniform? Because all the ones we've looked at so far have been uniform planks and things like that. Well, what if it's not uniform? So if it's not uniform, that just means the centre of mass is not halfway. So either they'll tell you how far along it is, or maybe you've got to work out where is the centre of mass. So let's draw a diagram for this question here. I'm just going to read the question and draw a diagram of it. So let's just read through it and draw a diagram as we go. So we've got a non-uniform rod AB of length 3 meters. Oops. Okay, so there's my rod, and then length is 3 meters. And it's got a weight 20. Now it's non-uniform, so I'm not going to put on exactly where that is yet. I'll hopefully do that in a minute. It is in a horizontal position resting on supports at points C and D, where A to C is 1 meter, so that's like a third of the way along. Okay, so this length here is 1 meter. And A to D is 2.5 meters. So that means that little length at the end is going to be 0.5 meters. The magnitude of the reaction at C is 3 times the reaction at D. So that means that this is 3 times the size of the reaction here. So I can write that. Find the distance of the center of mass of the rod from A. So if the reaction force here is much bigger than this one, that means the center of mass must be nearer to support C. Okay, so I'm going to put it about there. And the weight of the plank was 20 newtons. And that's what we're trying to work out is the distance of the center of mass from A. So that's from the end here. So we're going to call that X. This is A, this is B. Okay, so there's my diagram. Now we can just do all the things that we normally do. So let's resolve up and down. So we've got 3R plus R equals 20. So that means that R equals 5 newtons. So we've got that. And now we can take moments about somewhere. I'm going to do moments about A, just because that's where I'm measuring this distance from, so it makes that a bit easier. So moments about here, I've got 3R times 1 meter plus R times 2.5 meters. That must be equal to 20 newtons times distance X. Now I can solve this. So I've got 2.5, so what's that? 5.5 lots of R, so 5.5 times 5. So it gives me 27.5 on this side, 20x. So then x is 1.375 meters. There we are. So you can see that it's definitely not halfway. The plank was 3 meters long, and this is not halfway. It's a little bit short of halfway. Okay. So there we go. So you don't really have to do much extra work for a non-uniform one. You just have to be careful with how you label it, I guess. And I guess the main thing is don't accidentally draw it halfway. Okay, so it's worth maybe exaggerating it, because if you draw it here, you might just look at your diagram and think, oh yeah, that's halfway, and forget. So make sure you do draw it more to one side than the other. Okay, so exercise 4C and 4D are about these two different scenarios. I would suggest you just work on these questions, so maybe 8, 9, 10, 11 from 4C, which is about uniform planks, and then question 6, 7, 8 from 4D, which is non-uniform planks.